Alright, we're going to talk today about tapers, chamfers, and bevels in Unit 20. Basically, a taper is a uniform increase in diameter over a distance. It can be on a round part, it can be on a flat part, or whatever. But it's a gradual change as it goes up from the smaller up to the larger. Now, we're going to talk a little bit more probably about tapers that are on round parts today than anything else. Some examples of different types of tapers. For those that are in fundamentals or have had fundamentals, you're all going to know what a Morse taper is. Morse taper is a self-locking taper. It's a real slight taper that's on the end of a drill bit that holds a drill bit into a spindle on a drill press, or holds it into the tailstock on a lathe. Alright, they have a taper per foot of 5/8 taper per foot. When we say self-locking, then that means when you engage that taper with something else, it stays locked until you knock it out with a drift key or whatever. It's such a slight taper, it locks together with itself. A Brown and Sharp is a 1/2 inch taper per foot. Okay. Then we also have tapered pins, like a tapered dowel pin or a tapered pin that's going to drive into something. It's got a 1/4 inch taper per foot on it. And another one that we deal with a lot is a pipe thread. Pipe threads need to be self-sealing because they're piping liquids and gases and such things as that. Well, in order for it to be self-sealing, they have to be tapered, so the farther you screw that pipe thread in, the tighter it gets and it seals itself off. A pipe thread has 3/4 of an inch taper per foot. Now we're going to talk a little bit about taper per foot and taper per inch. If you look in your book, when you look in your book, it talks about determining taper per inch and taper per foot. That's on page 104. And I'm going to write it down a little bit larger than what you see in your book there. So we'll come back over here. And we're going to have a formula for determining taper per inch. And this is in your book. Okay? It says taper per inch equals big D minus little d over the length. Now, big D is going to be this right here, so we'll write big D right here. Little d is going to be your small diameter, and your length is going to be how long is that taper. And this is all in inches, so that means that's going to be taper per inch. Alright, so if I took 2 minus 0.5 divided by 3. Okay? And of course, if I go 2 minus 0.5, that's going to be 1.5. And I take 1.5 divided by 3. That's going to equal 0.5, but we take 1.5 divided by 3 equals 0.5. That means it's 0.5 taper per inch. That means for every inch, this diameter is going to change 0.5. It's going to change a 1/2 inch as it goes up. That is the taper per inch. Now, if you wanted to find taper per foot, you can take taper per inch times 12. So I could go 0.5 times 12 equals 6 taper per foot. So for taper per foot would be 0.5 times 12 equals 6. That's 6 taper per foot. Okay. That is how we figure taper per inch and taper per foot. That's the way you're going to see most of your tapers called out. For instance, if you look right here on this print, it's got 0.2 taper per inch. That means you could figure out over 2.5 inches, you take 0.2 times 2.5, and that's how much this diameter is going to change till it gets down to here. you can actually figure that kind of thing out. A lot of the times you're going to see something on there that'll tell what style taper it is and point right at it. Then you'll have to have a machinery's handbook or whatever to figure out what the actual taper per inch, taper per foot, or whatever it is that goes by that. Now, when we get over and we talk about other things, you can read through the rest of this stuff in your book. When we get into talking about chamfers, when it's 0.18 by 45, and we talked about this when we talked about angles, but if it's 0.18 by 45, that means it's 0.18 from here back to here on the taper, or 0.18 from here up to here because it's a 45. If you've got a 30-degree chamfer, then you got to really look at the length as to which way it goes, because it's not 0.18 in this direction. It's 0.18 from here back to there. You got to really look at how you lay that out. You got to really look at, if you were doing this on a compound rest on the lathe, you really got to look at what angle you're going to put your compound on to put that on there. So that's something to keep up with. Bevels, kind of the same way. And then they're actually showing an internal chamfer here. They're showing it as a countersink over here. You could actually do it that way. That's two different ways to dimension. Alright, so you'll do the unit on page 107. The only problem I see on this print is the line that they got going around representing this pad that's on the part should actually be a hidden line, because it should be on the other side of the part. Other than that, everything should be okay.